So I'm going to be explaining the simplex algorithm, what it does, how to use it, a bit about complexity. So yeah, let's get into it. What does it do? So the simplex algorithm returns an optimal solution to a linear program. So let's say you have some sort of function that you're trying to maximize. So here you're trying to maximize z. It will return the optimal solution, so the optimal values for x1, x2 and x3 in order to maximize z, given these constraints here. Okay, but in order to do this, you need to give the linear program what's called standard form. And what is standard form? The objective function, i.e. the function you're trying to maximize, needs to be a maximization, not a minimization. So in a real world situation, it'd have to be a profit, not a cost function. All variables have to have non-negativity constraints, only inequality constraints, no equality constraints, and all inequalities must be the same round. They will have to be less than or equal to, no greater than or equal to. So there are ways of changing any linear program into a standard form, and I'll get to those at the end. But let's just say you've got your linear program in standard form. You then need to turn it into slack form. So here we have it in standard form. Now to turn it into slack form, what we do is we add slack variables. Here I've added slack variables S1, S2 and S3. Now what slack variables do is they measure the difference between the left hand side and the right hand side of the equation. So if we add the difference between the left and the right hand side to the left hand side, we're going to get this left hand side plus the slack variable equals 14. So we know the left hand side is less than or equal to 14, but plus the slack variable is going to push it up to equal 14, and I think that kind of makes intuitive sense if you just look at this. Once again, it's pushing, the S2 is pushing it this side up to equal 28, the S3 is pushing this side up to equal 30. So once we have this, you can rearrange it and it will give you this slack form. Rearrange it, so now that you've got your slack variables on the left hand side and your other variables on the right hand side. Now the variables on the left hand side are what are called basic variables, and the variables on the right hand side are called non-basic variables. And we're going to be doing various operations swapping basic and non-basic variables, which we'll get to in the algorithm. And that's called a pivot, by the way. Swapping basic and non-basic variables is called a pivot. Anyway, so the algorithm itself. Convert standard form to slack form, we've done that. Find non-basic variable that can be used to increase the objective function. We're going to do that. Find type basic variable, swap non-basic and basic variable, find the original values. So don't worry if this doesn't make sense straight away. It will make sense after we do this first example. So it said we're going to try and find a non-basic variable that will increase the objective function. So what we're looking for is a non-basic variable that has a positive coefficient. So x1, x2 both have positive coefficients, so we can increase either one. So now we've chosen we're going to increase x1. And we're going to increase x1 as much as possible without breaking any non-negativity constraints. So we want to make sure we don't break S1, S2 or S3's non-negativity constraints. So how much can we increase x1 to before S1 becomes negative? So the answer is 7. Because 14 minus 2 times 7 equals 0. How much can we increase x1 in this equation? The answer again is 7. 28 minus 4 times 7 equals 0. And how much can we increase it to in this equation? 30 minus 2 times 15 equals 0. So x1 could be 15 in this equation, 7 and 7. So you would take the smallest, whichever equation x1 can be the smallest in, and you're going to use that. In this case, both these equations is the same. We're going to take the first equation, doesn't matter. So now we can do what's called a pivot. So we found the type basic variable, that's S1. We're going to pivot, which means we're going to swap. We're going to make x1 the basic variable and turn S1 into a non-basic variable. So we're going to rearrange this equation, putting x1 on the left and S1 here. And if you do that, you'll get this. And you simply replace this equation with this new arranged equation. Now what you're going to do is, you're going to replace these values of x1 here for your new value of x1. And you'll get something like this. So just simply subbed this in for the different areas x1 was. Simplify all that, and you get this. So now we have a new set of non-basic variables, x1, a new set of basic variables, x1, s2, and s3, and a new set of non-basic variables. Now we're simply going to perform the same thing again, second iteration. So which one of these non-basic variables can we increase that will increase the objective function? Can't increase s1 because it's got a negative coefficient. We can increase x2, so let's increase x2. Once again, we've got to find the tight basic variable. So how much can we increase x2 before x1 becomes negative? Well, in this equation, x2 can be 14, and that would make x1 equal to 0. x2 isn't in this equation. It was cancelled out. What does this mean? It means no matter what we change x2 to, it'll have no effect on s2 being negative. So it doesn't matter. We can ignore that equation. And what can we change x2 to be in this equation? The answer is 4. 16 minus 4 times 4 equals 0. So this is our tight basic constraint because it's the smallest. 4 is smaller than 14. So once again, we rearrange, we pivot, making x2 the basic variable and s3 the non-basic variable. If you rearrange that equation, you'll get this. And once again, we just put that there. Now once again, we're going to replace all our x2's with this new value of x2. And you'll get something that looks like this. Just literally sub this in for the different areas of x2. Rearrange it, tidy it up, and you'll get this, and this is our new thing. And now if we want to go perform a third iteration, we'd find that we can't, because all of our non-basic variables in our objective function all have negative coefficients. So increasing any of them is only going to decrease our objective function. What does this mean? It means we're done. We found our optimal solution. What you now do is you set all your non-basic variables, all the variables on the right hand side, equal to 0, and it will give you your answer. So we set all the variables on the right hand side equal to 0. We've got x1 equals 5, x2 equals 4, and x3 equals 0, which we've set equal to 0. And our objective function z equals 13. So this is our optimal solution for our original linear program. And that's how you do it. Quickly, I'm going to show you how you convert a linear program that's in non-standard form into standard form. So, if you have a minimize, 5x minus 4y, to turn it to a maximize, you simply negate it. So minimize 5x minus 4y is the same as maximize minus 5x plus 4y. If the variable doesn't have a non-negativity constraint, simply replace your variable y with two other variables, y1 minus y2, which both have non-negativity constraints. If an equality exists, so you have x minus y equals 7, you simply replace that equality with two inequalities. X minus y is less than or equal to 7, and x minus y is greater than or equal to 7. And if your inequality sign is the wrong way around, you just negate it again. So x minus y is greater than or equal to 7, like we've got here. You simply negate it, and you get minus x plus y is less than or equal to 7. Great. Now just a quick bit on complexity. Simplex is not a polynomial time algorithm. It's been shown to take 2 to the n iterations with n variables and 2 n constraints. But it has been shown that it can be on average can be bounded by polynomial time, and in practice it's very efficient. So this is my explanation of simplex algorithm. I hope you liked it, I hope it helped. Thank you very much.